This video clip will be for us to focus on some of the calculations to be done in the clock reaction with our day 1 data, which focused on the influence of concentration on the rate of a chemical reaction. Let's first take a look at problem number 7, where it asks us to determine the instantaneous rate of the chemical reaction using tangent lines. The reaction that we used in the lab, we had chemical A reacting with chemical B to produce some products. Chemical A, we varied the concentration of from trials 1, 2, 3, 4, 5, and so on. Chemical B, throughout the reaction, we kept at an initial concentration the same. The graph we're going to make then will focus on how changing the concentration of A influenced the rate of our chemical reaction. The graph we'll construct will be the concentration of A on the vertical axis versus time measured in seconds on our horizontal axis. The graph we create should appear to be something like this. Here we have our initial concentration of A at time 0, where the concentration is highest, and we can see that the concentration of A diminished as time went by. To find our instantaneous rate, what we need to do is pick several points along our graph, and we're going to find the tangent line at each one of these points on our graph. So what we would do is pick a point at this particular moment in time, draw our tangent line at that point, and then with that tangent line do a measure of our rise divided by our run that we have for the tangent line, and take our rise that we get here divided by our run for the tangent line, and that will give us our slope, and in this case the slope is equal to the rate of the reaction. Repeat the process, taking another one of our points that we have. We're going to draw a tangent line at that point, and we'll find what our rise is divided by our run, and when we take our rise divided by our run, that'll give us our slope at that point in time, which would be our instantaneous rate. This should be repeated at 3 different points on the graph. Next question we'll take a look at would be question number 9. Question number 9 will require that we go through a little background information in order to complete number 9. Chemical reactions have associated with them something known as a rate law or rate law expression. This would be a sample rate law expression. What this is, here we have what the rate of the reaction would be. K is something known as a rate constant. And then we have the chemicals A and B, which are our reactants. Up here we have exponents associated with each one of the reactants. The exponents are known as the order of the reaction. For example, here with the exponent 2, this tells us that this reaction is second order with respect to chemical B. What the order of the reaction tells us is how that chemical impacts the rate of reaction. In this case, when something is second order, what that tells us is if we were to double the concentration of B, the actual rate would go up by a factor of 4, which is 2 squared. The exponent of 1 for reactant A tells us that this reactant, we have its first order with respect to chemical A. Now what this tells us, again, the order tells us the impact chemical A would have on the rate of reaction. Something that's first order, if we were to double the concentration of A, since it's raised to the first power, the rate would also double. If the concentration of A were cut in half, the rate would fall by a factor of 1/2 when the chemical that is first order is being manipulated. Now the sum of the orders in a particular rate law give us the overall reaction order for a reaction. So this order, we'd say it's third order overall for this particular reaction, in that if we take a first order plus the second order, that adds up to be 3, and we'd say that the reaction overall is a third order reaction. Now a key thing with orders of reaction, both this first order and second order in this reaction, is that orders of reaction are determined by experiment only. Now this would be a key thing, once again, that the orders here that we have for a reaction are determined by collecting experimental data to see how that particular reactant will impact the rate of a reaction. The key thing again is that these orders of reaction are determined by experiment only. This is how to determine the values of the exponents in a rate law expression. An equation that can be used to mathematically determine the reaction order with respect to a particular chemical using reaction experimental data is to use this equation where we take data. We have our rate of reaction that we measure for trial number 2, which could be any trial, and then designated as number 2, and then we take the rate of reaction for a different trial we call trial number 1. If we take the concentration of trial number 2 divided by concentration of trial number 1 and raise that to the m power, when we solve this, our answer for m here would be whatever the order of the reaction is with respect to the chemical that we have the concentration of in this calculation. So we have to compare a couple data trials. We have trial number 2, trial number 1, the rates, concentration of trial number 2, concentration of trial number 1, raised to the m power. When we solve for the m here, that'll give us the order of the reaction with respect to the chemical that we used in the calculation. Let's take a moment and do a sample calculation using some fictitious data. We're going to use this data to try to figure out what's our order of reaction with respect to x, and also what's the order of our reaction with respect to y. What we need to do is pick two different trials. Now, to focus on chemical X, we have to make sure that we select trials where X is being changed but Y is remaining constant, so that we can see the influence on the rate for exclusively X. If we look in here, we can see in trial 1, X had a concentration of 1. Trial 2, X had a concentration of 2, but Y remained the same. So we can use these two trials to investigate the role or influence X had on the rate of the reaction. We also have what our rate of the reaction is for trial 2 and the rate of the reaction for trial 1. Our equation again is we're going to use the rate of the reaction for trial 2 divided by trial 1, and we use the concentration of X for trial 2 divided by the concentration for X in 1, and this will be raised to the m power. We want to solve for m, and that would give us our exponent for chemical X, or the order of the reaction with respect to X. Inserting our data that we have from our data table, for trials 1 and 2, the rate of the reaction is 2 for trial 2 over 1 for trial 1. Concentration of X was 2 over 1 to be raised to the m power. Solving for m in this case, m comes out to be 1. What this tells us is that this reaction with respect to X will be a first order reaction. We now can repeat the calculation, except now using concentration of chemical Y. We have to be sure to select reactions where chemical X remains constant. For example, we can come down here. We have our last two trials where chemical Y is being changed, but X is remaining constant. Let's select the last trial and use that as rate for reaction number 2. So our rate of the reaction would be 9. Reaction number 1 would be where our rate of the reaction is 4. We have our concentration of Y is going to be 3. Our concentration of Y for the previous trial is 2. If we raise this to the m power when we solve for m, that will give us the order of a reaction with respect to chemical Y. We need to use logarithms to solve the problem. By taking the log on both sides, that will allow us to move our exponent m down, giving us the expression the log of 9/4 is equal to m times the log of 3/2. Taking our logarithm, we have 0.352 equals m times 0.176. Dividing by 0.176 will give us our value for m. Solving for m, we get 2 equals m. What this tells us is that for this reaction, the order with respect to y would be a 2. This tells us this reaction is second order with respect to y, previous calculation told us it was first order with respect to x. To do this using the lab data, what we'd have to do is select and find our average rate from a couple different trials, take the average rate, designate that as trials 1 and trial 2, and you have your concentration of chemical A as well for trials 1 and trial 2, and calculate the order. Once doing that for those two trials, repeat the process picking two different trials. Make a trial 1, another one is trial 2, use your concentration for 1 and trial 2, compare those in the calculation and calculate another value for M. Once doing this for 4 separate pairs of trials, then average together the different the values for M you get to establish an average order for our reaction for chemical A. The goal being to try to figure out what's the order of reaction with respect to chemical A for the data we collected in our lab exercise. Once establishing what the average order is for our reaction with respect to chemical A, we can then do question number 10, which says calculate a value for the rate constant K. To do this, what we would do is we have our value for M from question 9. We can insert our concentration for chemical A from one of our trials, and then we also put in what the average rate is for that particular trial. We then solve for K for that circumstance. Repeat this several times, changing and using different concentrations of A, different average rates, calculate K for each one of those trials, and then average that value of K to get an average value for our rate constant for this particular reaction. For example, let's say hypothetically, from our data, let's say hypothetically that we figured out the order of our reaction was 2.5, which is possible to have fractional orders. The concentration we had was 0.003, and we found that our rate was 0.005 moles per liter per second. We can now solve for K using this data. Solving for K, in this case, we'd find that our rate constant would come out to be 1.014 times 10 to the 4th. This should be done using laboratory data to solve for K for our particular reaction.